Let's talk about the most familiar and yet maybe the most mysterious force in the entire universe, gravitation. Yeah, it's the reason an apple falls from a tree, but it's also the grand architect of galaxies. We're going to get into how this one fundamental force really does shape everything around us.
The answer, of course, is gravity. But look, this isn't just going to be some dry physics lesson. A deep understanding of this single force is literally what makes the map on your phone work. Stick with me, and I promise you'll see exactly how.
So, where do we even begin? Well, our journey has to start with the person who first gave us the language to even describe it all, Sir Isaac Newton. He's the one who created the first really powerful framework for understanding this universal attraction. So, what is gravitation really? At its absolute core, it's this force of attraction that exists between any two objects that have mass. You've got mass, the Earth has a whole lot of mass, so there's a force between you two. The sun and the planets all have mass, and that's the cosmic glue that keeps our entire solar system in order. It is truly universal. Okay, Newton's big idea really breaks down into two key parts, mass and distance. First up, mass. The more massive the objects are, the stronger the gravitational pull between them. Simple enough, right? But the second part, distance, is where it gets really interesting. The pull gets weaker the farther apart things are, but it's not a simple one-to-one drop. It follows what's called an inverse square law. So what that means is if you double the distance between two objects, the gravitational force between them drops to just 1/4 of what it was. Let's just do a quick rundown of its key features. First, gravity always pulls. It never ever pushes. It's also, and this might surprise you, the weakest of nature's four fundamental forces. I mean, electromagnetism is way stronger. Also, gravity doesn't care if there's air or water or a total vacuum between two objects. And, like we said, its rules apply everywhere. Okay, that's the cosmic scale. Let's bring this concept right back home. How do we experience gravity here on Earth? Well, it all comes down to a special little value we call g. Here's a question for you. We tend to think of our weight as this fixed, constant number, but is it really? The answer, which is kind of surprising, is no. Now, your mass, the amount of stuff you're made of, that stays the same. But your weight, which is just the force of gravity pulling on you, it actually changes a little bit depending on where you are on the planet. And here's the perfect illustration of why. The Earth isn't a perfect sphere, you know? It actually bulges out a little at the equator. This means that if you're standing at the North or South Pole, you are physically closer to the Earth's center of mass than if you were standing on the equator. And what did we just learn? Closer distance means a stronger gravitational pull. So yeah, you would weigh slightly more at the poles. This chart shows the really strange journey of g. It's kind of counterintuitive, but if you could magically stand at the very center of the Earth, you'd actually be weightless. Why? Because the planet's mass would be pulling on you equally in all directions, canceling itself out. As you move out from the center, that pull increases, and it hits its maximum right here on the surface at about 9.8 meters per second squared. And then, as you move away, say up a mountain or into space, the force of gravity starts to decrease again, just like Newton's law said it would. So we get how gravity keeps us here, but what does it actually take to break free completely? That question is the absolute heart of the physics of space travel. And the key concept here is something called escape velocity. This isn't just about going really fast, it's about hitting a very specific speed. It's like a threshold where you can finally overcome a planet's gravitational grip for good and not fall back down. For our planet Earth, that magic number is 11.2 kilometers per second. Just think about that for a moment. In the time it takes to snap your fingers, you've traveled over 11 kilometers. That's over 40,000 kilometers an hour. It's an absolutely incredible speed, and it is the minimum price of admission to the rest of our solar system. Okay, so once you're in space, you see astronauts experiencing something we call weightlessness. It seems like a totally alien sensation, but we can actually understand it with a really simple analogy. An elevator. Think about it. Your feeling of weight is really just the floor pushing up on your feet, right? Well, when an elevator starts to go down, that upward push gets a little weaker for a second, and you feel lighter. Now, just imagine the cable snaps. You and the elevator are both in freefall, accelerating downwards at the exact same rate, g. The floor isn't pushing up on you at all anymore. That feeling, that is weightlessness. And that's exactly what astronauts in orbit are doing. They are in a constant state of freefall around the Earth, which is why they float. But what if you don't want to escape gravity completely? What if you want to use it? Well, that's exactly what satellites do. They're not
fighting gravity. They're actually riding its pull.
So this is a really crucial difference: orbital velocity versus escape velocity. To stay in a stable, low orbit, you need to be going about 7.9 kilometers per second. You're moving so fast sideways that as gravity pulls you down, you continuously miss the Earth. If you go any slower, you fall back. But if you hit that escape velocity, 11.2 kilometers per second, you'll break away for good.
Now, there's a really special kind of orbit that is incredibly useful to us. It's called a geostationary orbit. Basically, a satellite orbits right above the equator and takes exactly 24 hours to go around once, the same time it takes the Earth to spin. So what's the result? Well, from our point of view on the ground, it looks like it's just hovering in the exact same spot in the sky day and night.
To pull off this amazing bit of celestial synchronization, a satellite has to be at a very, very specific altitude, nearly 36,000 kilometers up. It's this precise positioning that makes things like satellite TV and continuous weather monitoring even possible. And all of this, Newton's laws, orbits, velocity, it all brings us to the ultimate everyday application of our understanding of gravity, the Global Positioning System, or GPS. So how on earth does your phone do it? It's a really clever process called triangulation. Way up above you, there's a whole constellation of satellites, and each one is constantly broadcasting two things: its exact position in space and the precise time. Your phone's receiver picks up these signals, and it measures the incredibly tiny delay in how long each one took to get to you. By calculating its distance from at least 4 different satellites at the same time, it can pinpoint your location on the globe with amazing accuracy. But the entire system, the whole thing, hinges on perfect timing. Those radio signals are traveling at the speed of light, so even a tiny error in timing, I'm talking a millionth of a second, could throw your location off by hundreds of meters. And that's why every single GPS satellite has multiple, mind-bogglingly accurate atomic clocks on board. And while we often just call it GPS, that's technically just the American system. As you can see here, other major world powers have their own constellations of navigation satellites, like Russia's GLONASS, Europe's Galileo, and China's Beidou system. Your modern smartphone can probably use signals from several of these systems at once to get an even more accurate lock on your position. And that really is the main takeaway here. From Newton watching an apple fall to the satellites orbiting thousands of kilometers above our heads, it's all connected. That simple little map on your phone is the final result of centuries of work just to understand this one fundamental force of nature. We mastered gravity to navigate our world, and it completely changed everything. So it kind of leaves you with a big question. As we keep unraveling the secrets of the universe, what's going to be the next fundamental force that we harness to completely reshape our daily lives? Thanks for tuning in.